This problem is illustrative of the optimization of an idealized impulse turbine. The analysis determines the minimum penstock diameter needed to obtain a specific power output. In practice, larger diameters than this are used, reducing the frictional head loss below that computed here. Windmills, more properly, wind turbines, have been used for centuries to harness the power of natural winds. Two well-known examples are shown in Figure 10.42. Dutch windmills turned slowly so the power could be used to turn stone wheels for milling grain, hence the name windmill. They evolved into large structures. The practical maximum size was limited by the materials of the day. Calvert reports that based on his laboratory scale tests, a traditional Dutch windmill of 26 millimeters diameter produced 41 kilowatts in a wind of 36 kilometers per hour at a regular speed or an angular speed of 20 miles per hour. American multi-blade windmills were found on many American farms between about 1850 and 1950. They performed valuable service in powering water pumps before rural electrification. The recent emphasis on renewable sources has revived interest in windmill design and optimization. Horizontal axis wind turbine and vertical axis wind turbine, that is HAWT and VAWT configurations have been studied extensively. Most HAWT designs feature 2 or 3 bladed propellers turning at high speed. The large modern HAWT, shown in Figure 10.43a, is capable of producing power in any wind above a light breeze. The final example, Figure 10.43b, is a Darius VAWT. This device uses a modern symmetric airfoil section for the rotor, which is formed into a Tropuskian shape. In contrast to the other designs, the Darius VAWT is not capable of starting from rest. It can only produce usable power above a certain minimum regular speed or angular speed. It may be combined with a self-starting turbine, such as a Savorius rotor, to provide starting torque. A horizontal axis wind turbine may be analyzed as a propeller operated in reverse. The Rankine model of one-dimensional flow, incorporating an idealized actuator disk, is shown in Figure 10.44. The amplified rotation of the figure is frequently used for analysis of wind turbines. The wind speed for upstream is V. The stream is decelerated to V sub 1 at the turbine disk and to V sub 2 in the wake of the turbine. A is called the interference factory. Thus, the stream tube of air captured by the wind turbine is small upstream, and its diameter increases as it moves downstream. Straightforward application of linear measurements to a CV, or example 4, predicts the axial thrust on a turbine of radius r. The application of the energy equation, assuming no losses, that is, no change in internal energy or heat transfer, gives the power taken from the fluid stream The efficiency of a wind turbine is most conveniently defined with reference to the kinetic energy flux contained within a stream tube the size of the actuator disc. This kinetic energy flux is in the following equation. Combining equations 10.36 and 10.37 gives the efficiency, or alternatively, the power coefficient 401, as Betz was the first to derive this result and to show that the theoretical efficiency is maximized when A equals 1/3. The maximum theoretical efficiency is N equals 0.593. It is the wind turbine which is lightly loaded, that is, A is small. It will affect a large mass of air per unit. Most of the kinetic energy in the initial airstream will be left in the wake and wasted. Tough take.